Today, we are going to understand how virtual memory works. This is one of the most fundamental concepts in operating system. So let's get started with it. Let's start with the problem. You open 20 browsers tab, video editor, your IDE and many other apps all at the same time. Now your laptop has only limited RAM, let's say 8 GB. So how are these apps even running all at the same time? Or think about this. What if a program needs 16 GB memory but your system only has 8 GB RAM? How is it even running? Shouldn't it just crash? Next problem, if multiple processes are running, can process A accidentally read processes B's memory? Virtual memory is the operating system's answer to all of these questions. Now, let's understand what exactly is virtual memory. To put it simply, it is just an abstraction or an illusion which OS gives to every process that they have a large, private, contiguous block of memory, regardless of how much physical RAM is actually available on the machine. There are three key things that makes this concept very powerful. First is illusion, where every process thinks that they own all the memory space. Second is isolation, where where processes cannot access each other's memory. Third is flexibility, where programs can use more memory than is physically available on the system. Now, let's understand how this illusion is created. When a program runs, it works with virtual addresses. These addresses are generated by CPU, and every process starts from address 0. These virtual addresses do not directly correspond to any physical RAM location. The actual RAM location are called physical addresses and they are managed by the OS. Now, the job of translating this virtual address to a physical address is done by a hardware component which is called MMU, Memory Management Unit. It sits inside the CPU and does the translation on every single memory access. Now, the OS does not manage memory one byte at a time. That would be too expensive. Instead, memory is divided into fixed size chunks. Virtual memory is divided into chunks called pages. Physical memory, that is RAM, is divided into chunks called frames. Both are typically 4 KB in size. The important thing here is that pages don't need to map to contiguous frames in RAM. Each virtual page maps to exactly one physical frame in RAM, like page 0 maps to frame 2, page 1 maps to frame 7, and so on. But not all pages needs to be in RAM at the same time. Pages that are not being used can sit on disk in swap space. The OS keeps track of all of this through something called page table. The page table is a data structure that is maintained by the OS and there is one per process. It maps each virtual page number to the physical frame number where that page lives in RAM. Now, when you access a virtual address, MMU looks up the page table to find the corresponding physical frame. To make this faster, CPU also has a small cache which is called Translation Look Aside Buffer (TLB), which stores recent translations so it does not have to hit the page table on every single access. Each entry in the page table also has a present bit, the flag that tells the OS whether this page is currently in RAM or not. Which brings us to the next concept. When the CPU tries to access a page that is currently not in RAM, it triggers what is called a page fault. Here is how it works. The CPU accesses a virtual address. Then MMU checks the page table. If the page is not in RAM, a page fault exception is raised. Now OS takes over, finds that page on disk in the swap space. It loads it into a free frame in RAM, updates the page table, then retries the instruction. From the program's perspective, nothing happened. It just resumes. Now, there are two types of page faults. A minor page fault is when the page is already in RAM, perhaps loaded by another process, but just not yet mapped in the process's page table. In this case, OS simply updates the mapping, no disk read, so it is fast. Another kind of page fault is a major page fault when a page has to be fetched from disk, which is slow. Now, we mentioned about swap space. What is it? It is a reserved area on disk that the OS uses to store pages that have been evicted from RAM. So, when RAM fills up, the OS picks the least recently used pages, writes them to swap, and this is called paging out. It frees up those frames for other processes. Now, RAM is extremely fast, nanoseconds access times, but it is very limited and very expensive. On the other hand, swap is much slower, millisecond access times, but it is much cheaper and larger. So, virtual memory bridges these two together to give you the illusion of a larger memory than what physically exists on the system. So far, we have only discussed the benefits of virtual memory. But virtual memory is not without its problems. When it goes wrong, you get something called thrashing. Thrashing happens when the OS is spending more time swapping pages in and out than actually executing process instruction. The system becomes very slow. You have probably experienced this. CPU usage is at 100%, disk is going crazy, but nothing is actually loading. That is called thrashing. It happens when too many processes are competing for too little RAM. Every process keeps causing page faults, and the OS is stuck in this endless loop of swapping pages. Now, how do you fix it? You can probably add more RAM, kill unnecessary processes, or reduce the number of processes running at the same time. Let's put everything together. When a program accesses a virtual address, MMU looks it up in the page table. If the page is in RAM, it gets translated to a physical address and execution continues. If it is not in RAM, page fault happens. OS loads the page from swap space, updates the page table, and the CPU retries as if nothing happened. And if your RAM is severely overloaded, you get thrashing. The system keeps swapping without making any progress. And all of this together gives you process isolation, ability to run larger programs, and efficient multitasking, all managed by the OS using virtual memory concept. That's it for today's video. If this video helped you understand how the OS manages memory behind the scenes, hit that like button. If you have any questions or if you want me to cover any other topic, drop a comment below and subscribe for more such content.